So the next speaker is Petr Jizba, and yeah, you can also talk about quantum aspects, coherent states for generalized uncertainty relations, maybe as a new paradigm for Thales thermodynamics.
Yeah. So thank you for having me here today afternoon. And in my lecture, I would like to, as the title suggests, to address the issue related to coherent states for generalized uncertainty relations. Namely, I would like to emphasize the role that Thales entropy plays in this context. My talk basically consists from three parts. In the first part, I would like to mention some background about generalized uncertainty relations and coherent states. In the second part, I will try to show what role Thales entropy plays in this game, and I will show how to derive ensuing entropic uncertainty relations. And in the last part, I would like to show some universe cosmological implications by using Thales thermostatistics combined with Ferlinde's entropic gravity. So, I mean, currently it's pretty well known, quite well recognized that general relativity and quantum mechanics, in order to be reconciled, require some dramatic conceptual shift in our understanding of the space-time. Namely, recently there was a revived idea that space-time perhaps is really discrete or coarse-grained with the minimal length scale for the Planck scale. This is suggested by various quantum gravity scenarios that basically predict more or less the same basic minimal length scale. So a natural question that arises in this context is how the finiteness of the space-time grains modifies Heisenberg uncertainty relations. The question is quite obvious. Apart from the conventional scale that quantifies quantum fluctuations, which is the Planck constant, we have also extra scale, which is Planck scale. So there are various ways how one can modify Heisenberg uncertainty relations. And among those, particularly prominent is so-called generalized uncertainty principle, which makes sort of minimal modification with the modifying parameter or parameter beta, which just tells you that modification should be proportional to uncertainty in momenta squared. In fact, this relation is indicated from various resources, like from quantum gravity or string theory. In fact, if beta is positive, then you have region allowed region given by this bounding curve, which indicates that there is some minimal irreducible uncertainty in position, which is of course reflected with the fact that we have discrete space-time. On the contrary, if beta is negative, so the right-hand side cannot be smaller than 0 because left-hand side is positive. So that gives us the maximal value of uncertainty in momenta. I will be particularly interested in negative betas. And in fact, if you identify the delta with conventional standard deviation, that uncertainty relation might be derived conventionally from the deformed commutation relation through the standard Schrödinger-Robertson procedure, which you know from textbook. In fact, this relation this commutation relation is not so esoteric as it might seem, because in fact it appears in many effective condensed matter theoretical quantum mechanical systems, and it also appears if you have a constrained quantized system, because then you promote the Dirac brackets into commutators with non-trivial right-hand side. So this is something that people already saw before, not necessarily related to quantum gravity. So another concept I would like to emphasize are coherent states. In a nutshell, coherent states are basically quantum states that saturate Heisenberg uncertainty relations. They are, in a sense, the most classical because position and momenta are localized in those states as much as quantum rules allow. In fact, they have very particular properties. For example, they are the most robust with respect to decoherence. So they live longest out of all possible pure states. That's the reason why they are so popular in quantum information and quantum optics, because of this robustness again environment. They also, because of the fact that they live longest, they are typical states that you encounter while you are trying to describe a semi-classical description of quantum theory, which is on the borderline between classical and quantum description. But they're also used in order to describe quantum classical phase transitions or transitions to address such interesting phenomena like Schrödinger cut or entanglement, or this borderline between classical and quantum physics. So in this particular setting, maybe interesting question is, what about semi-classical limit of GUP-driven universe? How corresponding coherent states would look there? It's not difficult actually to find such coherent states. One can follow the conventional textbook derivation from, for example, Messiah textbook. So you use the Schwarz inequality, would like to make it equal. So you need to have that state P psi must be proportional to state X psi. In addition, the anti-commutator expectation value of anti-commutator on the right-hand side of Schwarz inequality must disappear. This automatically sets that C must be complex number, pure complex number, actually pure imaginary number. And this equation pronounced into equation for coherent state. Now one can go to momentum representation in which the position operator is diagonal, in contrast to position representation where momentum operator would be non-diagonal. You can plug it into this equation and you solve it. You just get ordinary differential equation, which is easily solvable. The solution is Pauli type coherent state with the normalization depending whether beta is positive or negative. In fact, when beta is 0, there is no deformation, conventional case, then this Pauli type coherent states turn out to be conventional Gaussian wave packet or Glauber coherent state. So this is Glauber coherent state in harmonic oscillator. So in order to uncover a little bit more the structure of the coherent state, one can change the parameters beta gamma to new parameters Q and B. So particularly when the deformation is 0, then Q equal 1 and Q is monotonic function of beta. And in those new parameters, the wave function coherent state has this form. Some of you might immediately recognize that this is nothing but probability amplitude for Thales distribution. Thales distribution is this object. So now Thales distribution has the property that it decays asymptotically as Pauli rather than exponential, which is quite bad because if you, on the first side is quite bad, because if you take variance or keep variance and mean as the only observable and try to use now maximal entropy principle based on Shannon entropy, then Pauli type of distributions are not following Maxent for Shannon-Gibbs entropy, as for example, Glauber coherent states do. In fact, the Thales states or Thales coherent states are extremizing so-called Thales distribution. This is this object. By having now entropy, identified entropy that is sort of pertinent in GUP, one can ask question, can I derive something like entropy-based uncertainty relations that would be sort of equivalent to variance-based uncertainty relations in the GUP framework? And the answer is yes. You can do that in the same way as in conventional quantum mechanics when you have standard commutation relation, representation of position and momentum operator in momentum representation. Corresponding eigenstates of those operators are just plane waves. So because you have plane waves, the arbitrary wave function in position space is related with wave function in momentum space through conventional Fourier transform. And then you can just use various inequalities in mathematics that connects those Fourier transform duals. For example, Beckner-Babenko inequality, which is valid for Fourier duals. You can arrive on so-called Shannon entropy power inequality. This is entropy power, Shannon entropy power. I'll show you shortly what it is. And it is basically more or less the same form as Heisenberg uncertainty relations. And indeed, in case of Gaussian distribution, this reduces to conventional Heisenberg uncertainty relation. Entropy power is defined through this identity, and this is Shannon entropy. So this is entropy power, which basically tells you that entropy power is variance of a would-be Gaussian distribution that is the same information, Shannon information content as the random variable X in question. So this can be solved uniquely. I find out that entropy power is just exponent of entropy. So this entropy power uncertainty relation is saturated only when the wave functions are Gaussian, so coherent states. And in addition, it shows you why Shannon entropy function has such a predominant role in quantum conventional quantum theory, and now mostly in quantum information theory. Similar procedure can be done with our deformed commutation relations. In that case, the position and momentum operators have this form. Eigenstates are not anymore plane waves, they are more complicated, although they are again not quadratically integrable. They belong again to space of Schwarz temperate distributions. And in fact, if you would like now to find dictionary between wave function and position representation and momentum, it's not connected via Fourier transform, but via so-called Abel transform. Again, you can go to mathematical textbooks and find what is if there are any inequalities between Abel transform duals. You can again find, there's actually a bunch of them. And again, you can be motivated by the success in the case of conventional quantum mechanics by using entropy power. In this case, it should be, however, the Tsallis entropy power. It should satisfy this identity, which means that it's a variance of the Tsallis, would-be Tsallis distribution that would have the same Tsallis entropy as the random variable in question. And again, you can find out that there is entropy power, Tsallis entropy power based uncertainty relation, which is valid now in this GUP framework. Again, this uncertainty relation is saturated if and only if the states are satisfying the GUP coherent state equation. This is true only for beta negative. And it also shows that in GUP framework, it's the Tsallis entropy function that is a pertinent functional that should be considered. In addition, if we realize that coherent states in GUP describe quasi-classical regime, then we could do the same business as we do, for example, in thermodynamics. We can take this maximal entropy distribution, plug it into entropy, and we obtain thermodynamical entropy. In case of conventional thermodynamics, you obtain thermodynamical entropy of Clausius. In case of Tsallis, you obtain the thermodynamical entropy of Tsallis. And ensuing the Tsallis thermostatistics, which goes together with it. So in particular, Tsallis thermostatistics seems to be very natural language in order to address the issue that describes the borderline between classical and quantum world in GUP-driven universe. So of course, this seems to be very natural to apply in very early universe when the quasi-classical regime should exist for gravity. And so natural question is, what modification of Newton law I should expect if I would be now in quasi-classical regime in early universe, GUP-driven early universe. And because I would need somehow to gravity derived from thermodynamics, a very natural framework is to use the Verlindes idea for entropy-driven phenomenon or entropy-driven gravity, coupled together with non-extensive thermodynamics of Tsallis. So I mean, this is something which maybe I don't need to even tell about, but this is a nutshell, very simple Verlindes paradigm, which can be, of course, much more sophisticated. So according to this paradigm, true microscopic degrees of freedom live actually inside of some holographic sphere, and we make inferences, our emergent world, which is outside of the sphere. So we make emergent world by making inferences based on the reading of information on the holographic screen. Holographic screen may be in the simplest form made as a sphere. And here is this typical force, entropic force, which was shown today in the morning session. And the conventional Newton force appears if you make those identifications like the dx is equal to Compton wavelength, which is the minimal distance on which you can still speak about single particle picture. When you have the equipartition theorem that energy inside of the sphere is proportional to number of bits on the surface, number of bits of the surface is through holographic principle related to area of the surface or with 4 times Hawking-Bekenstein entropy. You are also using Landauer erasure limit, which tells you that if you remove or erase one bit of information, it releases the heat into environment, which is proportional kBT. In fact, if you have Tsallis thermostatistics, only 2 modifications need to be made. This heat one form needs to be changed to Tsallis heat one form, and the Landauer erasure principle needs to be changed to non-extensive Landauer erasure principle. That's all you need. So now if you take L, which will be any characteristic length scale in the system, which is dimensionless, then Hawking-Bekenstein entropy should be proportional to L squared. And the asymptotic equipartition theorem from information theory tells you that you can always affiliate with such entropy number of configurations, which is related to logarithm of number configurations. So number of configurations should scale as some positive number to area. And here is some weakly dependent function phi on L. So weakly means in limit L goes to infinity should be satisfy this condition. So now we can take this number of states and plug it back into Shannon entropy, similarly as you do that if you plug number of states into Boltzmann entropy. You get Shannon entropy. Basically, from outside the holographic screen, you see that the holographic screen carries so much bits of Challis entropy. So now you use this prescription for entropic force. Now I make two things. I made expansion error Q close to 1, which is Q being close to 1, which was originally in the conventional quantum mechanics. And I take this function phi and I make something which is called the Hills expansion, which is typically thermodynamics expansion for small or mesoscopic systems. And I keep also term L cubed, which is not necessary to keep because we have scaling that goes with area, but we shall see that it will anyway be cosmologically forced to be 0. So now the Verlinde prescription combined with Challis thermostatistics gives you the entropic force and it gives you entropic potential. So entropic potential is very fascinating because it's nothing but a Mannheim-Casanas spherical symmetric solution or Schwarzschild-like type of solution for conformal gravity. In fact, for conformal gravity, R² term is purely vacuum solution. It's not coupled to any source. So you can basically erase it because it's not source dependent. And that K3 is related to omega 3, which was precisely this one. So it tells you that from cosmologically viable scenarios, this term cannot be there. Maybe as a footnote, before I go to conclusions, the Mannheim-Casanas solution fits wonderfully galactic curves. I mean, they tested that on more now than 200 galactic curves with no adjustable parameter apart from the mass to light ratio. So there is no need for dark matter in Mannheim in conformal gravity, Mannheim-Casanas solution. So in summary, I found that momentum coherent states for GUP-driven universe are Challis probability amplitudes, which should have the non-extensivity parameter between 0 and 5/3, which ensures that first and second moment is finite. And mathematically, those coherent states are something which are called minimal uncertainty coherent states of Schrödinger and Nieto. Entropic uncertainty relations induced by GUP offer a very natural theoretical arena for Challis entropy in this semi-classical or quasi-classical phase of GUP-driven universe. In addition, if I couple that with the maximal entropy principle, this allows me to use basically all the framework of Challis thermostatistics to address, for example, modification of gravity in this quasi-classical region. You can put various numbers inside. I mean, I have some we have some predictions. We recently have rapid communication in PRD related to this paper. So we, for example, found that Q should be indeed very close to 1. This is different Q, 1 minus Q. So 10 to minus 15 is really justifying our expansion in 1 minus Q. And the beta, the deformation parameter is 10 minus 3, which is precisely the value that is also proposed by string theory. So I would basically end up here.
We have also time for 1 or 2 questions. Right? Yeah. Dan, Manus?
Yeah, so can you go back to your formula for Challis entropy at the end? Yeah.
You mean this form?
No, at the end where you talk about Verlinde's here.
Yeah.
So how should I think about this formula in the middle? Because you...
This formula is basically, if I would take now Q goes to 1, which would be no deformation, I would get just logarithm of number of states, which is Boltzmann entropy.
And then you get the area law.
And then I would get area law because the V precise thing scales in this way.
But for Q not equal to 1, what does this mean?
That means that I'm describing the, I'm now looking on the holographic screen, but I don't look on, let's say, I don't look on a normal thermodynamic entropy, but I look on Challis entropy, which means that there's different number of bits. Challis entropy is an object that is, of course, different from conventional Shannon entropy. So it doesn't carry so equal number of bits as Shannon. So it's the deformed number of bits.
But does it also correspond to some geometric quantity like area plus some corrections?
Yeah, of course you can find, of course, if you plug this there, then you find out here is the formula. So if you go with L to very large values, then you see how it scales it. In fact, if you have logarithm if you have logarithm of 1, it's precisely normal logarithm. So this is the deformation of logarithm. This is called deform or quantum deformed logarithm, which is appearing in quantum deformation context. So this is deformed logarithm. So you can see the scaling if you go with, let's say, q close to 1, and if you take L being very large, then you get the scaling, which in this case, of course, it's not area law, but in the limit when q would go to 1, it would precisely. You can even make expansion in q minus 1 to see precisely how this scales, and you would get behavior. Actually, it's maybe better here. You see that the area law basically appears with this term when it can go to
what is the first order correction then?
The corrections are typically something like 3/2 are typically fractional corrections.
Right, thank you.